Before we get started, I need to give a massive thank you to Linode for sponsoring this video. They make it easy and affordable to host your site or service in the cloud, offering no-nonsense hosting with plans starting at just $5. This means no surprise fees or overages like you might have gotten from some more entry-level hosting companies. Now, Linode also has a full API that works with tools like Terraform and Kubernetes, making it an awesome environment for development projects. Maybe you've used an entry-level hosting service before. Well, Linode is your step up to powerful, fast, and fully configurable cloud computing. Anyways, go ahead and sign up with the link below and take advantage of a free $20 credit using the code TWT19. Alright, so let's talk about binary search trees. Now, before we get into the search tree part of this, let's discuss what a binary tree is. Now, most people know a tree is usually comprised of what we call nodes connected with branches. So if I'm drawing one on the left side of my screen here, we have nodes. Maybe this node has a value of 1 and it has some branches coming off of it. Now, usually these can just be arbitrary. There can be like a random amount of branches. Maybe these ones have a few branches coming off them. Maybe this one has one and it keeps going, right? And that's what a tree is. Now, a binary tree is really basically just a tree that only has at most 2 branches for every node. Now, what that means is each parent node has at most 2 children. So if you say this is the parent, which we'll say is P, then I guess I'll just write them right on here. These are the children, right? And it has at most 2. It can have none, it can have 1, but it can have at most 2. And that's all a binary, or I guess a binary tree is. It just has 2 children for each parent. So now if we call this one the parent, it can have at most 2 children. And you can keep going and each node has at most 2 children. That's all a binary tree is. So you can see this big tree that I've written in the middle of my screen is a binary tree. And that's because at most we have 2 children to each parent node. So if you say this is the parent, you can see we have child 1 and we have child 2, and then the rest of them only have 1 child. Now, a child is just the node that kind of precedes or comes after, or I guess is connected to one of these parent nodes. And that's kind of some terminology I'm going to be using here now. Now, this is called the root node. Now, the reason it's called the root is because it is the start of our tree. It has nothing that comes before it, and it's actually the only node in our tree that has no parent, so we call it the root. That's important because I'm probably going to use that terminology a few times. So anyways, that is the root node. I'll just erase that for now. Okay, so now that we know what a binary tree is, what is a binary search tree, also known as BST? Well, a binary search tree now satisfies another property. Not only is it a binary tree, but it also is a search tree, which means that we can find elements in it very quickly. Now, the way we do this is because every child that's connected to this tree is connected in a specific way. So looking at our root node here, we can see that the left child, which would be this one here, so 5, is always less than the root node. So you can see 5 is obviously less than 7. And 8, which is our right node, is always greater than the root node. So the way this works is when we add in new elements, based on where we're adding them in the tree, they're always going to put themselves in some kind of order so that it's very quick and easy to find certain elements in the tree. So if you look at 5 here, you can see that 2, since it's less than 5, goes to the left of it. And 3 over here, since it's greater than 2, it goes to the right of it. And that is kind of the way that we add elements in and the order that we maintain in this tree. So having that property satisfied where every left child is less than the parent and every right child is greater than the parent is what makes this a search tree. So those 2 properties combined gives us the binary search tree. All right, so let's start discussing how we can actually create one of these trees. So I'm just going to erase a few nodes here so that I can add in some more ones. But let's say we have a tree that starts off looking like this. So we have that root node is 7, then we have 5, then we have 8, then we have 2. Well, how do we add elements into this tree? Well, what we do is, let's say we have the element 9, and we want to add it into this binary search tree. Well, when we add it, we need to make sure that the same binary search tree properties are satisfied to keep this a binary search tree. So what we do is we compare it, first of all, to the root node. And we say, okay, is this value greater than or less than the root node? In this case, it's greater than, so we move to the right. Now, if there was no root here, or sorry, not root, if there's no node here, we would just add 9 in. So we could replace like where 8 is with 9 if 8 wasn't there. But since there is one here, we need to figure out where we're putting this based on this node. So we look at 8 and we say, is 9 greater than or less than 8? Now, since it's greater than, what we do is we move to the right again. We see that there's no node here, so there's room for us to place 9. And we put 9 right here as the right child to 8. And that's how we add elements into our binary search tree. Now let's do another example with the element 3. Now you already know where 3 goes because you saw me show it, but let's do kind of the process of how we add it. So let's say we want to add 3 into this tree. Well, we do the same thing. We compare it to 7. We say, is it less than or greater than? It's less than, so we go to the left. Is there room for 3 yet? No, there's not. So we compare it to 5. We say, is it less than or greater than 5? Well, it's greater than 5, so we go to the right. Turns out there's no other node there, so we can go ahead and add 3. And now, or sorry, what am I saying? What do we put going to the right? Sorry, we go down to 2, we go to the left because it's less than 5. Yes, I'm thinking correctly. And then we say, okay, is it less than 2 or greater than 2? It's greater than 2, so we add it as the right child to 2. My apologies on that one there, guys. So that is how that works, and that's how we add elements into the binary search tree. Now this is pretty straightforward, so let's just start by constructing one from scratch to make sure that everyone understands how this works. So our nodes, just going to do a quick note here, have a value, they have a left node, so a node that's attached on the left, and they have a right node. Now when we start off our tree, we don't have any nodes, so what we do is, let's say we want to add the numbers 7, 5, 9, 3, 2. These are the numbers that we want to add into our binary search tree. How do we do this? Well, we start with 7, and since there's currently no nodes in our tree, 7 immediately just becomes our root node. So we write 7 here, and we throw that one like that. Now 7's gone, we've added that one into the tree, now we move on to 5. And now we repeat the process I've just talked about. So we say, okay, let's compare it to 7. Is it less than or greater than 7? It's less than, so we're gonna add it right here to the left of 7. And this is what's gonna be now the left node of the value 7, or on the node 7, this is the left child. All right, so that's how we do that. Now let's add 9. Okay, so we compare it to 7. We say, is it greater than or less than? Well, it's greater than. So we go ahead and add it to the right side here. And now we have 9. Okay, 9's gone. Now it's time for 3. All right, so let's add this in now. So we look at 7. We go to the left because it's less than. We look at 5. Go to the left because it's less than. And we add 3 like that. And now let's keep going. And let's add 2. So when we do 2, we do the same process here. We go left, left. Oh, it needs to go to the left again. And then we add 2 right there. Now let's add in one more number just to show kind of how this works. So let's say we want to add 6 now. Well, I'm just going to erase some of these lines. Let's do the same process again. Compare it to 7. Is it greater than or less than? It's less than, so we go to the left. Compare it to 5. Is it less than or greater than? It's greater than. So we go to the right and we add 6. And that is how we construct this binary search tree from scratch. The first element just immediately becomes that root. And then from there, we just compare it to each node. We say, do we go to the left or do we go to the right? And we keep going through there until eventually we have room to add in our node. Now, this is just basically how it works. So let's talk about kind of more of an implementation of this now in code, because this has all been kind of abstract. So let's just erase some of this stuff down here. So the reason I wrote this node thing here on the left side of my screen is so that we know what each of our nodes have. So what we're going to do is in our program, we're going to set up an object. It's going to be called node. What we're going to do is each node in our binary search tree is going to have a value, which could be, 7, 5, 9, whatever it is. And it's going to have a pointer to a left node and a right node. So essentially what happens here is we actually store this node in, the left property of 7. And we actually store this node, which is 9, in the right property of 7. So when we actually want to loop through and look through our binary search tree, we can do this recursively. All right, so what I'm actually going to do now is program an implementation for a binary search tree. I'm just going to do this in Python. Before I used to write these out, but I was finding that it's getting kind of messy and my handwriting obviously is not neat enough to do like long bits of code, which is kind of what we need to do here. So I'm just going to do some kind of pseudocode, Python-y like programming of a binary search tree. So the first thing that we need to do is create a node class. So I'm going to say there's a class node. It's going to have a few properties. So we're going to say define ___ init underscore underscore. And what we're going to do in here is simply define a value for this node. So we'll say self, we'll say value, and then what we're going to do is add some attributes. So we'll say self.value equals value, self.left equals none, and self.right equals none, like that. Now let me just save this as a Python file. So it's called test.py, because we're probably not actually going to run this. Let's save it like that. So anyways, that's what we have. We have this node class, and this is really all we need for our node class. We have a value, and we have a left and a right. Now the next class we're going to write is going to be called BST, or binary search tree. Now what binary search tree is going to have is just simply one property. So we'll go into init underscore underscore, and then in here what we're going to do is simply just define a root. So we're going to say self.root equals none. Now what this is going to mean is essentially when we first create our new binary search tree, there's nothing in it. And this root node is the only thing that we actually want to keep track of in our binary search tree. It's going to start off at none, but what the root node is that first node in the tree. So when we actually start adding elements into the tree, what we're going to do is the first element we add will become that root node. And then from there, that root node will have a left and a right, and then all those other nodes will have lefts and rights. And we can access those nodes by going to the left of the root node and the right of the root node and so on. So that's why we only need to hold a root node here in BST. Now the first method that I want to program here is going to be an add method. And the add method is going to, well, add a new value into our binary tree. Now what we're going to take in here is current, and we're also going to take value for what value we're adding to our search tree. So what I'm going to do in here is just kind of start programming this, and then hopefully I'll walk you through this as we go through it. The first thing we need to check when we add a new node into our tree is if we have a root node or not. So what I'm going to do is I'm going to say if root, actually I'll say if not root, which means, you know, like if root is equal to none. So I guess I can simplify that and just say if root equals none, then what we're going to do is just simply make whatever this value is a new node that is going to be the root. So we're going to say self.root, which I guess this needs to be self, is going to be equal to a new node, and in here we're just going to put value. So what this is going to do is construct a new node, as we can see here, and we're going to store that as the root node. Because we don't have one yet, that's what we need to do. Now otherwise, what we're going to do is actually write kind of a recursive method of finding out where this node needs to go, because it needs to be in the correct sorted order. It needs to be either to the left of the root node or to the right of the root node, and then after all those children and everything, it needs to be in the correct order. So we're going to start by checking if value is less than, in this case, current.value. Now I should say here that what current is going to keep track of the current node that we're looking at, because I'm actually going to make this method recursive. You're going to see how that works in a second, but current is going to start off as the root node for our binary search tree. So it's going to start as that root, so maybe we say that value is 7. We're going to compare the value that we're trying to add to that root node to start, and then do something with it based on if it's less than or greater than. So if the value is less than, what I'm going to check is if current.left equals none. Now, if it does equal none, that means, and I'll do a quick illustration here so that we can see kind of how this works. So we have this root node. Let's say maybe this is 7. I'm just drawing with my mouse, so give me a break here. We compare it to 7, you know, and we go now. We want to add our node. We check if the left of 7, if it's null or not, or if it's none. If it is, what we're going to do is just add the node in there. So let's say we wanted to add 3. Well, we'll just put it there. Now, if it's not none and there is a node here, then we need to do something else. So anyways, let's get out of this. Oops, I did not mean to do that. Okay, so if current.left equals none, then we're going to say current.left equals node value. And that's as easy as that is to add the node on the left side of the tree. Now, if it's not none, what we're going to do is we're going to say else self.add current.left value. I'm going to discuss what this does in a second, but let's move on to the next one here. All right, so if we've compared our value and it's not less than the current value, then it must be greater than or the same. So in this case, I'm just going to do an else statement, and I'm going to say else, and I'm literally just going to copy this, but change this to the right side of my tree. So in this case, I'm going to say if current.right equals none, then current.right equals node value. Otherwise, self.add current.right value. Now, let's walk through exactly how this add method works to make sure that everyone's on the same track here. I'll get my drawing tablet back out so that this is a little bit neater when I'm drawing. All right, so let's go back into this. Okay, so let's say we have a search tree and it looks something like this. We have 1 and we have 3, or I guess that can't really be 3. Let's make this a 7. So that's a 7, that's a 3, and let's say this is a 9, like right here. And I want to add the value 2 into my search tree. Well, let's go through kind of this method that we just wrote here and figure out what we would do. So we're going to pass current is going to be the root node to start. So whatever the root is, which in this case is actually just going to be 7, right? And then we're going to pass the value 2. So what we're going to do is we're going to say if self.root equals none, does it? No, it doesn't. So we'll move on to the next else statement here. We're going to say if value is less than current.value. So if this value 2 is less than this value 7, which it is, we're going to say if current.left equals none, does it? No, it doesn't. Then what we're going to do is call this method again with now the new current node being current.left and the value being again 2. So we're going to come up here and call this again. But now if I can get my eraser out and just erase some of this stuff, this is no longer going to be root. This is actually going to be the left node of root, which is going to be 3. So now the current node we're looking at is 3. The value is still 2, and we run this method the exact same one more time. We check, is the root equal to none? Obviously, no, it's not. Then we come here to the else statement. We say if the value is less than current.value, well, is 2 less than current.value? Yes, it is. So we go into here. We say if current.left equals none. Is it? Yep, the left of 3 is none. So what we do is we now add in our new node, which is 2, and that goes in the correct place. And we could do this for any example, any number, and this will work properly just because of the way that I've written that. So I hope that makes sense in terms of that implementation to you guys. Fairly straightforward. All right, so I want to quickly discuss here how long this method will always take to run. So essentially, like, what is the time complexity of adding a new node into our binary search tree? Well, I'm hoping you guys can probably come up with this on your own, but it actually runs in what we call log base 2 of n time. Now that means that this runs very, very quickly, and kind of the bigger that our, I guess, binary search tree is, the faster this actually ends up running in terms of like how much better the speed is getting. So if I just draw, I'm just going to make this a bit thicker here. If I draw a little graph down here, I'll just draw what the log function looks like so you guys can actually see at least the positive side. It looks something like this. So essentially, if this is time, so this axis here, and this is n, which means how many things we have in our binary search tree, as n increases, time very slowly increases, which means that this works really well for massive amounts of information, because as n gets larger and larger and larger, time actually stays fairly consistent and stays pretty similar. And that's why we end up using these types of data structures, because it's so fast to add elements in as well as to look for elements, which is what we're going to do next. But the reason this runs in log base 2 of n time, and I'm just going to erase some of this so that I can show you, is because of the way that we store things in the binary search tree. So let's just show a very basic search tree here. Let's say this is 7, this could be, I don't know, 3, this will be 4, we'll have a 1 here. I just need to have a few branches so that we can actually do a decent example. Say this is 11, and this is 8. Okay, sweet. So this is our binary search tree. Now let's say I want to add in the element 5. Well, what's the process of doing this? Well, we first start by comparing 5 to 7. And when we compare 5 to 7, we immediately know whether we need to go to the left of 7 or to the right of 7. And in this case, we need to go to the left. So what we actually end up doing is eliminating all of these nodes here from what we possibly have to search through on the binary search tree. So we've essentially cut the tree in half. And we've also eliminated 7 actually, because we no longer need to look at that. Now what we're doing is we just have this smaller tree that we need to look at. So we now compare 5 to 3, and we see is 5 less than 3 or greater than 3? Well, it's greater. So what we actually end up doing is cutting off this entire left branch here of 1, and even cutting off 3 as well. And now, again, we've cut this binary search tree in half. So this smaller one that we were just looking at, we've cut it in half. And now we're left with just this box here, I know this is messy, of 4. And what we do is we either go to the right or the left, and there we go. And then we cut off 4 and we're done. We've done that in pretty much 3 different operations. Now, as the tree gets larger and larger and larger, we still don't have to do that many operations because we keep cutting the tree in half and in half and in half and in half until we get to where we need to go. And that's why that runs so quickly, and that's why it's log based to event. I hope you guys can kind of understand that. I'm not going to go into much more detail about that. All right, so traversing a binary tree. Now there's 3 main ways to do this, and the first way we're going to talk about is what's called Preorder Traversal. Now, you also have Postorder and Inorder, but Preorder is kind of the most intuitive, I usually think, and these are pretty straightforward. Now, the first thing to talk about here is we have some kind of idea of visiting a node. So typically when we traverse or look through a binary search tree, we're trying to do something. We're either trying to find a specific node, or we're trying to, print out all of the nodes or collect all of the nodes. We're doing something with them. Now, when we actually do whatever operation we want, maybe we're checking something or we're adding something to a list, we call that visiting. So when we actually visit the node is very important because that is kind of how this traversal works. Now, the first order, which is called preorder, simply means, and I guess I'll write it here. Actually, what am I doing? Visit, go left, and then go right. This is what this stands for. Now, it's pretty straightforward. Essentially, what we do is when we're looping through the tree, we start by visiting the root node, which is this one, so we visit it. Now, when I visit a node, I'm just going to write it on the bottom of my screen so you can see the order in which I'm doing things. So 7 is the first node we visit. Maybe we're looking for a node, we check if that's a node we're looking for, whatever it's doing, we visit it. Now, what do? We go left. All right, so let's go left. So what we do now is we go left and we go to 5 and we repeat this process of this preorder traversal on this node 5 now. So even though it says go right as the next step for 7, we need to first do 5 because we've just gone to the left. So what we do now is we visit 5, which means I write it down here. And then what do? We go left. So we move left again and we visit 3, which means I write 3 down here as if we've been to 3 already. Now what do? We go left. Well, when I go left here, there's nothing here. So what I do is I move on to the next step, which is go right. So now I go right and I go to 4. Okay, so now we visited 4. All right, so now that we've done that, what do we need to do? We need to kind of go back up the ladder and go right because we've just finished going left. So essentially from 7, we went left to 5. We visited 5. We went left from 5 to 3. We couldn't go left from 3, so we went right. And now we've gone as far left as we can go. So we start coming back up. And we go, okay, we go to 5. Well, we went as far left from 5 as we can go. So now we go right and we visit 6. And now, well, we've go back up to 7 because we've gone as far left as we can go. And what do? We now go right and we go to 12. So now we visit 12. And from 12, we follow this process. We visit, we go left, and then we go right. So we visit it, and now we go left to 8, which is here, and we've followed this process. So we visit it, we go left, we go right, and we can't do anything there. So we come back up to 12, and now we say, okay, we've gone as far left as we can go. We couldn't go right, so now we go right over here to 13, and we follow this process. We go left, and we go right, and once we've reached a point where we've pretty much completed this process, we are done and we have traversed the entire tree, and that is what we call the preorder traversal. So visit, go left, and go right. So once you end up going left, then you follow the same process on that left node and continue and continue and continue until you can't go left anymore, and then you start slowly going right and moving your way back up the tree. If you simply follow this process, visit, go left, go right, you know to do preorder, and that is how that works. Now give me a second to clear the screen, and I'll be back with Inorder. All right, so what is Inorder Traversal? Now this is similar to Preorder, just a little bit different. What we do is we go left, visit, and then we go right. That is the Inorder Traversal, and you guys are going to see why we might do something like this as I start to write down the nodes that we're visiting. So we always start at the root node. Now we're starting at 7, but notice that I'm not going to write 7 here yet because I haven't visited 7 yet. So when I visit it, that's when I write it down. I haven't visited it. So the first thing I do when I get to 7 is I go left. So I go left here to 5. Now when I go to 5, what's the first thing I do? Well, I do the first step here in the Inorder Traversal, which means I go left. When I get to 3, what's the first thing I do? I go left. Now I can't go left from 3, so what's the next thing I do? I visit it. So I write 3 down here. Now, what's the next process after visiting? Well, it's going to the right. So what do? I go to the right. Now from here, I follow the process. Left, visit, right. Left, can't do it. Visit, right, can't do it. Come back up. Okay, so let me just get rid of these arrows here, just because I don't want to have them. All right, so there we go. So we go to 4, then we come back up. Now we've already visited 3, so we go to 5, and what's the process? Visit 5. Because we had already gone left from 5, right? So now we visit 5, and now what do? We go right. So we go to 6 now, which is here. And what do? We left, visit right. Well, we can't go left, we can't go right, and we visited in between there. So now we have 6, and now we come back up to 5. We've gone right from it. 5 is done. We're at 7. Now what do? We visit 7 because, we already went left. Now we're back here, so we visit, and now what do? We go right. And what do we do from 12? Well, we start, we go left. So we go left here. This guy goes left, visit right. So we visit him, 8. Then we come back up to 12. We visit because we've reached 12 again. And now we come over to 13. We go right, we visit 13. And there we go. That is the Inorder Traversal. And notice this gives our numbers in order. So left, visit, right. Now, if you wanted to go from greatest, like the largest number to the smallest number, you could do right, visit, left. And that would give you the opposite order because you would go as far right as you could, and then you would work your way back going left, and you would get this kind of flipped. So you'd have 13 at the start and 3 at the end. Anyways, that is how the Inorder Traversal works. I'm going to clear my screen and I will be back with Postorder. All right, the Postorder Traversal is kind of the opposite of Preorder. So in Preorder, we had left, right, visit, we had visit, left, right, and Postorder, we have left, right, visit. So what we do here is follow the same process that we've done before, except we go left, right, visit. So we go left, all right, we're here at 5. Now what do we do when we go to left? We go left. Now what do we do when we get to 3? Well, we can't go left, so what do? We go right. Now from here, we go left, right, visit. So we write 4 because we can't do anything from there. So we visit 4 as the last step. What do? We come back up to 3 here. And now what do? We visit 3 because we had gone right. So we write 3 here. Now we come back up to 5. We go right because that's how we had just gone left to go to 3. So now we go right to go to 6. We go left, right, visit. So we write 6 here. Now we come back up to 5. We can finally visit 5 because we had just gone left, right. Now what do? We come back up to 7 and we go to the right. So now we go 12. What's the process here? Left, right, visit. So we go left here to 8. Obviously from 8, we can't go left or right. So we need to visit, which we do. Then we come back up to 12. What do? We don't visit yet. We go right because we had just gone left. So now we're going right. So we go 13. Obviously, we can't go anywhere from here, so we just visit it. Now we come back up. We can finally write 12 because we just went left, right. And now, finally, back up to 7. And because we had gone left, right from 7, we can write 7 at the end, and that is our Postorder Traversal. Notice that you're always going to get your root node at the very end of your Postorder Traversal, and that is just the way that it works because left, right, visit, and since this was the first node to repeat that process, not until everything else is visited are we going to visit that root node. Now, there's different uses for all of these. I'm not going to talk about kind of what those are. You can figure them out as you go. But now I'm just going to quickly show you an implementation in actual code for this, and then we're going to wrap up the video, and hopefully you've learned a bit about binary search trees. All right, so what I'm going to do here is just quickly program the Postorder, Inorder, and Preorder Traversal. They're really straightforward. You're going to see how easy they actually are. And just notice I've created a visit function here which is going to stand for what happens when we visit the node. And in this case, I'm just going to print whatever the value of that node is. All right, so what I'm going to do here is start by doing preorder. So we're going to say preorder as the name of our method here. It's going to take self, and it's going to take, I guess, current as the node that we need there. All right, so what we're going to do inside of preorder is simply follow the process of visit left right. So what we're going to do is we're going to say visit, and in this case current. So I'll say self.visit, so this is proper. And then we're going to go to the left and we're going to go to the right. So to do that, we're going to say self.preorder like that. And then we're going to go current.left like that, and self.preorder, and in this case current.right. Now this is all we need to do for preorder. And why does this work? Well, exactly what we've shown before. So current is going to always start off as the root node. So what we're going to do is we're going to say self.visit. We're going to visit this root node, so print that out because that's what visit does here. Then we're going to go to the left of the root node and call this preorder function on the left of the root node, which is now going to pass whatever that left node is. We're going to visit it, and then we're going to go to the left, and we're going to go to the right. And this is recursively going to call itself and do the preorder. Now, I'm just going to copy this and really quickly show you postorder and inorder, but it's just a matter of moving around some of the statements in here so that they follow the correct order. So I guess we'll do inorder here. So inorder is just going to mean we're going to go left, visit, right. So let's move the left up here, and that's all that we need to do. And postorder, we'll simply put the visit at the bottom and change this name to postorder like that. What am I doing here? Like that. And then obviously, I mean, we need to change these to be postorder and inorder, but you guys get the point here. That is kind of how that works. And that is all that we need to do for the implementation. I'll just change these because it's going to bug me if I don't. And that is kind of how we can traverse through a binary search tree. Now, there's tons of things you could do with a binary search tree. I literally could have made this video like 10 hours long of the amount of different problems you can solve and how it works, but I wanted to give you guys a good fundamental understanding. I know that this was long, but I really need to explain how all of these things actually work. And I mean, now you guys should hopefully have an idea how you can, well, add an element into your binary search tree and how to kind of loop through it in preorder, inorder, and postorder. Now, there's tons of other things you might want to do, like delete, find, search, all of that. But I'm going to leave that to you guys. With this knowledge, you should be able to do that. And as always, if you guys have any questions, don't hesitate to leave them down below. That has been it for this video. I hope you guys enjoyed. Please leave a like and subscribe if you did.